Testing 1 2 3. Hello. Hi. Mic is working. Oh, I realize why I'm so zoomed in. I mean, 2 in the front. Good time of day. Whether it is morning. Oh wow, hi. Hey, what's up? Yes. Just sometimes I forget to fix the mic, and today I guess I didn't. What's up? Thank you so much for helping me with sometimes even when you're not with me live, you're still helping me with your comments, so I appreciate that. Oh yeah, cool. You're from Twitch. How's this stream from Twitch? It should be bearable. or maybe it's still a slideshow, but I hope not. Okay. So. Wow. So many cool people are here today. You are also a live person. We have people live here with us. Thank you for being here. Good Friday. I hope it's going to be a good Friday, inshallah. It's not it's a game, but I don't treat it as a game. This place where I'm getting this character from, this hijab was super expensive to buy, and I bought it because I thought why not? Okay. Yes. Where are we? We are sharing the screen. Oh, alright. So, yeah. Recap time, I suppose. We are taking this machine learning for coders on the fast.ai platform that's taught by Jeremy Howard. And, if you didn't know, it was course based on lessons recorded in University of San Francisco for a master's in data science program. Yep. And we are in lesson 9, almost at the end. And as we did sort of talk about L1 versus L2, but I don't know how in depth it went. And yesterday I was I had 15 minutes left, and there was no talk about anything NLP. So I don't know what the second half of lesson. I didn't see it as NLP. We were talking about matrix multiplication. Anyway, so let's see.
Okay.
If you want some practical things, Andre Karapathy has some videos that seem pretty good on YouTube. I like Andre Karapathy because he's like a famous researcher, but I haven't seen his videos. I mean, I'm gonna finish search. Hey, what's up? Wait, dude. Okay. I was going to YouTube. Why didn't I know that he makes videos that are like this. I thought he's just a researcher, you know? Which one do you recommend that I check out? The spelled out intro to language modeling? That seems interesting. I think this is like the first video, right? Oh, there's also this. Oh, there it is. Neural networks. Ooh. Intro to neural networks and backpropagation. Okay. I still want to finish this one before I move to anything else, but I didn't realize Andrej Karpathy makes videos that are like tutorial style. I just know he's a really famous researcher. That's right? Like, even if you Google him, yeah, he comes up. Ah, do I know about him because of Feifei Li? Maybe. Or like, yeah, he was working at OpenAI. Thank you. Building ones also go through building and training models, and I'm guessing these long videos. Oh, building, the one that says building. Oh, here's this one says building. Building part 2, which means this is part 1, and 3 and 4 and 5. Cool. Yeah, thank you. But you mentioned you were nearing the end of this course. You're right. It might help you as a start to look to hack on your own models. I mean, thank you if you think I can do anything good, but yeah, I'm just playing around. Not really even playing around, I'm just looking around. Yeah. Thank you.
Now, why would we want to do that? Well, obviously we don't.
What? What we don't want to do? What are we talking about?
And so that's broadcasting. And so what we can do with this now is use...
Sorry. Was something that we... bad bitrate, unstable internet, what the hell? Great, lovely. I think you guys should be able to hear me. Maybe? Yes? Okay. Yeah, broadcasting, which is something like I learned if two arrays are not the same dimension, how to, summarize them or multiply them. So that's what he was talking about yesterday.
Okay. Now, why would we want to do that? Well, obviously we don't, right? Matrix multiplication has already been handled perfectly nicely.
Is it loud? It feels a bit loud.
For us by our libraries. But very often you'll find in all kinds of areas in machine learning, and particularly in deep learning, that there'll be particular types of linear function that you want to do that aren't quite done for you, right? So for example, there's like whole areas called like tensor regression and tensor decomposition. which are really being developed a lot at the moment, and they're kind of talking about like how do we take like higher rank tensors and kind of turn them into combinations of rows, columns, and faces. And it turns out that when you can kind of do this, you can basically like deal with really high dimensional data structures with not much memory and not much computation time. For example, there's a really terrific library called Tensorly, which does a whole lot of this kind of stuff for you. So it's a really, really important area. It covers like all of deep learning, lots of modern machine learning in general. And so even though you're not going to like define matrix multiplication, you're very likely to want to define some other slightly different tensor product, you know.
Okay.
So it's really useful to kind of understand how to do that. So let's go back and look at our matrix and our 2D array and 1D array, rank 2 tensor, rank 1 tensor. And remember, we can do a matrix multiplication using the @ sign or the old way.
I didn't know, yeah, you can do the @ sign, but that's pretty cool. Or you can, yeah, use a function.
np.matmul. Okay. And so what that's actually doing when we do that is we're basically saying, okay, 1 times 10 plus 2 times 20 plus 3 times 30 is 140, right? And so we do that for each row, and we can go through and do the same thing for the next one and for the next one to get our result, right? You could do that in Torch as well. We could make this a little shorter. Okay, same thing. Okay, but that is not matrix multiplication. What's that?
There is no, I thought there's an, oh, it is the output. Wait, how is, tensor, I don't know. Oh, whoa. Oh, it's like the not result, I don't know. Put it all togetherification.
Okay. Element-wise, specifically, we've got a matrix and a vector, so broadcasting. Okay, good. So we've got, this is element-wise with broadcasting. But notice the numbers it's created, 10, 40, 90, are the exact 3 numbers that I needed to calculate when I did that first piece of my matrix multiplication. In other words, if we sum this over the columns, which is axis equals 1, we get our matrix vector product. Okay?
Okay.
So we can kind of do this stuff without special help from our library. So now let's expand this out to a matrix-matrix product. So a matrix-matrix product.
So up until now we've been dealing with rank 1 with rank 2, but now we're gonna check 2 rank 2s?
Looks like this. This is this great site called Matrix.
That's cool. Yes, so this is 3 by 3. Shoot. Oh, what did I do? Lights went out. Lights back on. Broadcasting. They just, yeah, I suppose. The idea is that if it's a 3 by 1, let's say, let's go back. yeah, like this one. I mean, this is just showing us M is a 3 by 3. C is 3 by 1. And he just showed that this deals with this, and then this with this with this, and then again this with this. And the idea is, if you go back again, I am not great at explaining, but he writes it, go 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 go. How far? Oh, nope. Yep. No, still. Oh, okay, still go back. There, this thing. It says if the two dimensions are well, if they're not compatible, we do this trailing dimensions, where what we do is like a oh, this is not math. This is just matrices are not really that math. It's regarding matrices, shapes and multiplication. Their shapes should have the form N, M, and MP. The result is yes, NP. Yes. I'm trying to explain that, but I'm doing it really bad. And it just clicked my be casting in programming, but broadly, I don't know. But he actually explains it really well, and I will go back because I do want you to understand it, and not see it as scary math thing, okay? And then we'll go to the we'll go back there.
The product?
Yeah.
So you see, we have here we're looking at an array, and he's converting it to like a, this is 3 by 1 and then this is 1 by 3, right? So he's saying we can do that. And how can we this is multiply, right? Yeah, how can we get the result of these two? What happens? So
10 cross 10, 20 cross 20, and 30 cross 30. And if we multiply the first row with this column, we can get the first row of the matrix.
I think I should go back to when he's discussing the idea of when it's a 1. He's discussing it really nicely. Yeah, yes, there. Should be here. I'm trying to explain it, but I'm like, no, I can't hold a candle to Jeremy Howard's explanation, so that's why I'm going
so
back.
Let's check, right? We've got our M and C compatible. M is
We have
3, 3.
no.
C is
Stay.
3. Right? So we're going to start at the end, trailing dimensions first, and check.
Trailing dimensions means, it's if it's a NM, we look at M first. This rule thing he wrote out. These two should be equal, and one for now, one of them should be 1.
Compatible. They're compatible if the dimensions are equal. Okay, so these ones are equal, so they're compatible. Right. All right, let's go to the next one. Uh-oh, we're missing. Right? C is missing something. So what happens if something is missing is we insert a 1. Okay, that's the rule. Right? And so let's now check. Are these compatible? One of them is 1. Yes, they're compatible. Okay? So now you can see why it is that NumPy treats the one-dimensional array as if it is a rank 2 tensor, which is representing a row. It's because we're basically inserting a 1.
Yeah, but the 1 is already there. Like, an array is a number by 1, or, the 1, it's already 1. It's not 0.
The front. Okay? So that's the rule. So, for example, this is something that you very commonly have to do, which is you start with like an image of like 256 pixels by 256 pixels by 3 channels, and you want to subtract the mean of each channel, right? So you've got 256 by 256 by 3, and you want to subtract something of length 3, right? So yeah, you can do that, absolutely, because 3 and 3 are compatible because they're the same, right? 256 and empty is compatible because it's going to insert a 1.
Yes.
256 and empty is compatible because it's going to insert a 1. Right? So you're going to end up with, this is going to be broadcast over all of this axis, and then that whole thing will be broadcast over this axis, and so we'll end up with a 256 by 256 by 3 effective tensor here. Right?
And then I'm gonna go back to the one where he's doing the there's
Visualize from 30 cross 30 column. We can get the first row of
and
the
we're looking at how this 1 by 3 3 by 1 would get
matrix.
how we
So
get the
finally
result.
There's broadcasting rules.
Okay.
Matrix.
Yeah. And so to think of this in terms of like those broadcasting rules, we're basically taking this column, right, which is of rank 3, 1, right, and this kind of row,
1 by 3.
sorry, of dimension 3, 1,
Yeah.
and this row which is of dimension
Oh wait,
1,
really?
3,
Ah.
right? And so to make these
I was saying this is a 3 by 1, this is a 1 by 3, but you know, you get it. Scalar could be thought of as broadcasting it. You're broadcasting the scalar one because you're making it look bigger for the other higher rank. That's what it means. And if we can get a you know, definition of broadcasting. What happened? Okay. Let's say matrix definition, maybe, if we can get one. The term broadcasting describes how NumPy treats arrays with different shapes during arithmetic operations. Smaller array is broadcast across the larger array so that they have compatible shapes. So it just makes it bigger. Yeah, operation of matching dimensions of differently shaped arrays. I gotta mute myself because I need something, sorry. Okay. Where were we?
compatible with our broadcasting rules, right? This one here has to be duplicated 3 times because it needs to match this.
Both of them this time will get broadcasted.
Okay, and now this one's going to have to be duplicated 3 times to match this. Okay, and so now I've got 2 matrices to do an element-wise product of. And so, as you say, there is our outer product. Right? Now the interesting thing here is that suddenly, now that this is not a special mathematical case, but just a specific version of the general idea of broadcasting, we can do like...
It's the norm in matrix, you know, operations. So you see here 10 by 10, 20 by 20, 30 by 30, but, you know, all over.
an outer plus, or we can do an outer greater than, right? Or whatever, right? So it's suddenly we've kind of...
Is it easier to understand now? Or did I not help? Where were we?
This, you can basically like deal with really high dimensional data structures with not much memory and not much computation time. For example, there's a really terrific library. Your other slightly different tensor product
Needs to be covered as it extends to the tensor. Yes, but the style that it is made bigger is like it's like row with row and again row with row. So the elements that go together, but it feels logical the way it happens.
So let's go back and look at our matrix. And
Did we check? Oh yeah, we did. Sorry.
Let's expand this out to a matrix product.
Oh, there. Okay.
This great site called matrixmultiplication.xyz, and it shows us this is what happens when we multiply two matrices. Okay, that's what matrix multiplication is, operationally speaking. So in other words, what we just did there was we first of all took the first column with the first row to get this one, and then we took the second column with the first row to get that one. Right? So we're basically doing the thing we just did, the matrix vector product, we're just doing it twice. Right? Once with this column and once with this column, and then we concatenate the two together.
Okay.
Okay? So we can now go ahead and do that like so. M times the first column dot sum, M times the second column dot sum. And so there are the two columns.
Why are we doing it manually?
Columns of our matrix multiplication. Okay, so I didn't want to like make our code too messy, so I'm not going to actually like use that, but like we have it there now if we want to. We don't need to use torch or numpy matrix multiplication anymore. We've got our own that we can use using nothing but element-wise operations, broadcasting, and sum. Okay. So this is our...
I'll be right back again, sorry. Yeah. So I just realized that I gotta go, even though I haven't been for here long, but it's okay. I guess I reviewed the matrix things. I had really forgotten the multiply one, and this matrix multiplication website was really cool to look at. So that was cool. Sorry I didn't really help that much, but why are you having trouble recognizing my face? But yeah, I hope it was helpful just a bit. And I gotta run, but hopefully see you tomorrow if all goes well. So, and yeah, I'll try to finish this. I'll try to finish this lesson tomorrow. Yes. So thank you for being here, and see you next time. Yeah, I'm gonna end in 5 4, 3, 2, and 1. Goodbye. Thank you. Bye.